So today I'm here to talk about sonifying your presentation for accessibility, and I'm Clara Brasseur. I'm currently at the University of St. Andrews, although this was work I did at the Mikulski Archive for Space Telescopes, and I'm also the lead developer on Astronify, which is the sonification package I'm going to talk about today. So before we really dive in to the meat of the presentation, what is sonification? So sonification is representing data as sound. So not data that is sound. We're not talking about like whale song or bat sonar, things that are inherently sonic. We're talking about, say, the light from a star or the rotation of a galaxy that is not inherently sonic, but that we're representing data as sound. So the thesis of this talk is that sonification should be ubiquitous at meetings. This talk is based around sonifying specifically with regards to presentations. So every plot shown on a slide should be accompanied by a sonified version, but this is absolutely not true. And why not? And there are a number of reasons. There are some technical reasons and more sort of societal reasons. So tools aren't widely known and easy to use. But also speakers don't generally feel the need who in the audience would benefit, which of course creates this terrible cycle where people who would benefit aren't in the audience because the talks aren't accessible, and then it continues. I'm not going to talk so much about that side of it. I feel like everyone who comes to this conference is very on board with why we want to make presentations and scientific communication more accessible. So I'm going to talk about the technical challenges because they're not trivial. Even if everybody decided tomorrow that this is something we all want to do, it's not simple to make it happen. The main reason is that creating sonifications is like creating visualizations. It requires practice and effort. Just because you know how to use plotting software doesn't mean that the first plot you made is particularly effective and gets across the point you're trying to express. And sonification is the same. It takes effort and practice. And no single tool can sonify everything well, so you need a constellation of options. However, we need well-publicized, well-designed, user-friendly sonification tools that most importantly need to be designed by and in collaboration with blind and visually impaired developers and scientists. And there needs to be associated training resources for creating sonifications, the way that we have tutorials and classes and books about creating effective visualizations. We need the same counterpart for sonifications. So in this talk, I'm going to talk about one software out of many. So this is the software project I'm involved in. It's Astronify. This project is open source Python code based. So the code is on GitHub. The documentation is on Read the Docs. It is designed for community driven development. It's currently out in beta, so you can install it from the PyPy repository. And it's open for issues and pull requests and contributions. And this code was written in collaboration with a huge number of different blind and visually impaired, both astronomers and developers who helped at every step of the way in terms of figuring out how to make this the most useful, not simply specifically for our target audience, which is blind and visually impaired scientists. This is a code base that is designed to be used for scientific analysis and presentations. And so with that in mind, we were very careful to integrate it into standard workflow. So this is why it's written in Python. It can be run from Python scripts and interpreters. Python is the most common programming language in the astronomy community. So it's important to be able to sonify right along with other standard analysis things. So what does Astronify do? Astronify is a package that was designed around sonifying light curves. So here on this slide, I have a plot that has time on the x-axis and light on the y-axis, so brightness from some sort of object. And there's a sort of sinusoidal type curve that has first a peak where it gets brighter and then a dip where it gets dimmer. And so when we turn this into a sonification, the brightness light turns into pitch, and the brighter part of the curve becomes higher and the dimmer part becomes lower. So here's the sonification associated with this plot. And before I continue, can someone verify that I shared my computer audio correctly and you all heard that?
Yes.
Great. Okay. So we can hear in that sonification what you can also see if you're looking at this plot, which is that you can hear that rising up to a higher pitch, which corresponds to more light, and then dimming down into a lower pitch. So here's an example of how to create a sonification with this software. So on this slide is an image of the code I used in its entirety to create a very simple sonification. So I am using the Astropy table class to create a simple data table that has 2 columns, time and flux, both containing the numbers 0 to 10. So a very simple straight line. Then I use the Astronify Soni series class, which is the class that encapsulates sonifying data series. So we create a Soni series object with the input of the test data table. It is looking for columns, time, and flux. However, you can tell it to look for other columns. I'm then setting the note spacing and the note duration. So the note spacing is the average note spacing. It's the length of time between different notes, and that is scaled based on the time values. However, the note spacing allows you to change that average, do an overall scaling, and decide how fast basically you want the sonification to go, but it will still be scaled by the time data, so you don't lose that dimension. So I set that to 0.2 seconds, and then the note duration, every note plays for the same duration, 0.3 seconds. Then we call the sonify method, so that's just .sonify. And then if I was doing this in Python interpreter session, I could do .play and listen to it right there. But since here we're trying to create sonifications to use later for a talk, I did .write, and it writes it out as a WAV file. So then here I import that WAV file into my presentation, and on the screen is the plot. So it's time on the x-axis, flux on the y-axis, and there's a straight line, and then we have our sonification of this plot. So you can hear that really rising tone, very smooth, simple rate. So that's just an example of how to use Astronify. So as I mentioned earlier, no one software tool works for everything. So what is the niche for Astronify? So Astronify is best suited for sonifying line plots. This was a project that came at the Mikulski Archive for Space Telescopes. So it was optimized for data that MAST holds, namely light curves from the TESS and Kepler missions. It's under active development, particularly to explore using it for broader swaths of data. Contributions are always welcome. This is very much a project that is limited by the amount of time developers have. We have far more ideas for what we want to do with it than what we have time to implement. And due to that nature, it needs to be used in conjunction with other audio processing software for more complex plots. And I will point out when I do that throughout this talk. So what can you do with it? So here I'm going to sonify some plots from a recent talk that I gave on stellar flares. So before we start, some caveats. So this is not the entire talk. I wanted to do that. I wanted to go through a full talk, but there just wasn't time. And Astronify is not suitable for sonifying everything. I did select plots with that in mind. And also one of the reasons that Astronify is focused the way it is, and the reason that I'm the lead developer on it is that it works very well for my science. So that is also not an accident, that it's more easily used for the type of science that I do. Easy to use yourself as a guinea pig. And I used Audacity for any additional audio processing. That is a free audio processing tool. It's just the one I use. You could use anything. So we'll start off with a simple plot that is right in the wheelhouse of Astronify. So this is a flaring light curve. So what I have is a GALEX light curve. GALEX is a space telescope, or was a space telescope, that observed in the near ultraviolet. And I have a light curve that is at a 10-second cadence. So each time bin is 10 seconds. And what we're looking at is a stellar flare. So that is a basically an explosion on the surface of the star, where you have a fast release of heat and light. So if we listen to this, so both listening to this and also looking at the plot that I have on this slide, you can notice that it starts off with, there's some noodling around. There's definitely some variation in the amount of brightness, but it's pretty constant. So that's the quiescent flux. Then in a very sort of classic flare shape, it does a fast rise. So it shoots straight up and then it falls back down in an exponential way that is slower. So that is that. Obviously, if I were giving a science talk, I would now explain why I care. But instead, we're going to talk about how I made that sonification. So on this slide, this is the code I used to make that sonification. So I used, again, the Astropy table functionality. I read in my data table. My time column and flux column are not time and flux. And I'm not actually showing in the plot or the sonification the entire light curve. So I give the part of the light curve I want to sonify to the Soni series object. I tell it that I want my time column to be t underscore mean, my value column to be flux underscore bg sub. So that's the background subtracted flux. I tell it that I want the note duration to be 0.8 seconds and I want the note spacing to be 0.04 seconds. Then I sonify it and write it out to a wave file. That's all. And then that's directly what we just listened to. So moving on to a more complex plot. So this talk that I gave, I was looking at stellar flares, and I was looking at stellar flares in the GALEX near ultraviolet, like the one that I showed, but also flares where we had data in Kepler, which is a telescope that observes in optical. So flares have generally are modeled with two components, line emission and black body emission. And the black body emission is taken to be 9,000 Kelvin. And so that gives you a particular curve. And so what I'm showing on this slide is a plot that shows a black body curve. So that's wavelength on the x-axis and flux density on the y-axis, overplotted with the GALEX waveband and the Kepler waveband. So when we listen to this, we'll hear that underlying curve and then a higher pitch that denotes where the GALEX telescope observed, and then a lower pitch where the Kepler telescope observes. So two things are noticeable. The first is that the Kepler telescope observes over a much broader band of wavelengths. But what's more important for my research is that the GALEX NUV, we can hear that it is close to where the peak of that black body curve is. And so that just means that the near ultraviolet in this telescope is a great place to look to observe flares in, because you get a lot of flux. So this was a little bit more of a complex plot to sonify because there's two lines. And because Astronify does not sonify two lines at the same time yet, what I did was first I have a simple table that's just lambda, so wavelength and flux for the black body. I sonified that using a 0.05 note spacing, saved that out to a wave file. Then I added another column for the telescopes that simply had one value where GALEX was observing and another value where Kepler was observing, and then a dummy value in their very first row to make sure that all of the timing matched up. This is another thing that I would love if Astronify would do natively, but it does not yet. So I then wrote that to another wave file and used Audacity to manually mix them into a single track and suppress that dummy value. And that turned into the sonification that I just played you. So the last plot that I'm going to talk about, it's really two plots. And this is the one that really starts to get into the meat of the science I was doing. And so what we have here is another GALEX flare, not the one I played before, a new one that has simultaneous Kepler data. And so we have two plots on top of each other, one that where they share an x-axis. The x-axis is again time, the y-axis is flux. And so if we play them together, this is what we get. So that long tone throughout is the Kepler data, and that chirp right in the middle is the Galax flare. So what we can hear right away is that we have a vast data cadence mismatch. The Galax flare is the 10-second cadence. That whole flare happens within one time bin for Kepler, because the Kepler data is at a half-hour cadence, because it's the long cadence. So if we pull out that Galax flare and just listen to the Kepler data on its own, there is we can't immediately tell where the Galax flare was. All of the Kepler data points. So what we're hearing is both the Kepler data and the quiescent flux, and you can't really distinguish them because they're not really distinguishable. You can't. There's no spike in the Kepler flare Kepler data that corresponds to the flare. But if we pull out the Galax flare and zoom in on it, which I've done in an inset on the plot, and I will play separately as a sonification, we can hear that it really is a flare. So it's not as clear and beautiful as that very first flare I played for you all, but you can definitely hear that shape, that sharp rise. And so what we have here is a Galax flare that's very clear and a Kepler non-detection. That's primarily because of this data cadence mismatch. And there are lots of interesting things we can say about that, but I will leave that for a different kind of talk and talk about how I made the sonification instead. So the way I did this, and I'm not showing all of the code here because there's too much of it, but it is in that GitHub repository that I put in the chat. So first I sonified each line individually, which includes both the Galax plot, but for the Kepler, it was the band that is the calculated quiescent flux as well as the data values. And then I mixed them together using Audacity, so my external audio processing software. So this allowed me to also easily have the get the plot with and without that Galax chirp on top. But it did involve a fair amount use of external audio processing software. And so it brings up two of the near-term goals I have for Astronify, which is to allow the sonification of multiple data series together, and to also allow for a non-zero starting offset so that we can get that alignment easily within the software, because alignment is so important in terms of truly expressing the data correctly. So that is basically my presentation. What I have on this slide is the documentation for Astronify is at astronify.readthedocs.io. That has all of the documentation, links to how to install it, how to use it, where the code is, and various other examples of it. And then the link to my GitHub for this talk. So that has in it the PowerPoint that I'm showing now, as well as all of the sonifications I created, the data files that went into those sonifications. I pulled out off extraneous columns, but I didn't do anything else to the data compared to what I actually had in my science folder, and the code that will create it all. I'm happy to talk about this. Obviously, I'll be taking questions in a second, but I'm also happy to talk about this whenever. I love talking about it. So my email is here. It's cb432@standrews.ac.uk. And also I'm on Twitter at CE Brasseur. Happy to take any questions.
Thank you so much, Clara. And please feel free to add those to our social media contact list that John spoke about during the opening. We can put that link in the chat for you to add. It's essentially just a list of everyone's contact info, so everyone can stay in touch after the conference.
Yes, great. I will definitely add to that.
Awesome. So I want to give questions a minute to come in, but with that, I have a question of my own. So it seemed like the coding you're doing, all of it's in Python, at least for the
yes,
sonification of your data. Is that something where you need to run Python in a specific visualizer, or can you do that with anywhere that uses Python? I know as an undergraduate student, I've used online databases that run Python? Is this something where you're going to be able to call the sonification
Yes, that's
application,
a
or do we
really,
actually need to install it before doing this?
okay, so that's actually a really interesting question. So yes, and I wish it can be a little bit complicated. And I've discovered that this is anytime that you're accessing sort of the sound card in your computer, it gets a little bit, unfortunately, more complex. So you can call it from any way of accessing Python. Like when I'm prototyping, I often use Jupyter notebooks, but all of the sonifications I made for this, I just ran a script. You can also do it in a straight up Python interpreter. In terms of doing it online, so in general, if you want to have the interactive aspect where you're playing sonifications right there from within Python, you have to do it on your own computer because it can't access your computer's sound card the same way. And so it can't play those sounds for you. I'd love to find a way around it, but I haven't. In general, and I haven't, this again, it depends on how they're set up, but usually you can do the sonification and write out the sonification and get the wave file that then you can pull down and play however you want, no matter where you're doing it. But unfortunately, the interactive aspect where you listen to it right as you're coding it does depend on having the correct linkage between the code and your computer's own audio stuff. And that's a bit more fragile.
Jupyter notebooks were exactly what I was imagining with that question. So that
So if you're doing a Jupyter
explains it a
notebook
lot.
on your own computer, you can absolutely do this. I actually discovered I'm currently running a Windows computer, and I have both Python installed directly on Windows and on the Windows subsystem for Linux, which is basically a virtual machine within it. And if I do it within the Linux subsystem and open a Jupyter notebook, it can't find my audio software. It can't play it. But if I do it directly from my Windows version, it does. But both of them will save out the results. So
very interesting. Thank you very much. We have a hand raised for a question. Arigaros, you are allowed to talk to ask your question.
Hello. Thanks very much for the presentation and for the work. I'm working on astrophysics myself, and I'm visually impaired, and I cannot tell you how useful is that and how I think forward is going as a society of scientists. For me, when I go to a conference, it's mainly I really lose a lot of information. It's sometimes really a waste of time to be to talks when you have no access to the plots and the graphs that people present. So thanks again for that. And another idea would be for people also to include when they upload documents in archive the papers, and you put the tech file and all the figures. An idea would be to also include the audio files with relevant names. So each graph has an audio file like that, and then I can download the source folder and then also listen to the graphs. That would be amazing, just as an idea.
That is a fantastic idea. That's a fantastic idea. Yes, that should absolutely be a thing. Thank you.
Yeah,
Thank you so much.
Again.
Okay, give me one moment. Thank you again, Argyros, for that comment and discussion. Obviously, this is such an important topic, and the reason why SciAccess is here is to make these sort of presentations more accessible and to also teach that accessibility is important. So thank you so much for that comment.
And I just wanted to add back to the GitHub thing. If you're someone who's using this software and you're not someone who's like a programmer or like very interested in contributing to open source software, we would still absolutely love to hear your opinion. If you want something added, you can open an issue or tell us. You don't have to be able to like provide it. We're always interested in feedback. Things are not always going at a fast pace because of time and effort limitations, but yeah, I'm very interested in how people use this and what's missing as much as what people like.